Good morning. I'm actually nervous to talk after Mark and Gianfranco. I will focus more on the multi-messenger aspect here. And so, active galactic nuclei are, of course, the most powerful sources in the universe, and as such, they are good candidates for producing all the messengers. This talk, I won't talk about gravitational waves, I'll talk about cosmic rays and neutrinos mostly. And so my plan is first to talk about the most rare and powerful AGM, jetted AGM, so they form about 10% of AGM, and then about non-jetted AGM. And then I think it's interesting to the Astro-COLIBRI community, so I'll briefly also mention tidal disruption events and some recent interesting observations there. Okay, so for an astrophysical source to be a good multi-messenger accelerator, there are certain, necessary but not sufficient requirements, but some of them are, attaining high maximum energy in particles, being able to accelerate to high energies, then sufficient emissivity. Yeah, usually that's not an issue, at least for AGM. For jetted tidal disruption events, this could be an issue. They're relatively rare. And then if we want to explain ultra-high energy cosmic ray observations with a particular source population, then we usually require a good fit to the diffuse spectrum and to the composition-related observables for the extensive air showers. And then for neutrinos, we have only the spectrum, so we require a good fit to the spectrum. And also, usually, there are stacking analyses now that have been done for the most major source classes, and they pose very strong constraints in some instances, like in GRBs, which are more or less excluded as good, the major neutrino sources in the ice cube energy range. So, concerning ultra-high energy cosmic ray emission from jetted AGM, which I will start with, usually here, I don't want to say there is a consensus, but a lot of people are comfortable thinking that these are good candidate sources. So this was articulated in terms of a minimum luminosity, minimum magnetic luminosity requirement already in the 70s and formulated more detail in the 90s. And so people then relate that requirement in terms of magnetic luminosity to some observations, which might be, in this study, the luminosity of the lobes, or as they did in this study, the cavities, because they were interested in what happened in terms of cosmic ray emission in the past in these sources. And the general conclusion here is that there are several sources, like Fornax A, M87, that Cygnus A, within our GZK horizon that can reach energies up to 40 exavolts. So there are good candidate sources here. And observationally, if we look at the arrival directions of cosmic rays above 40 eV, there has been an excess in the direction of Centaurus A, so there are 60 excess events. This is something that has been growing steadily for a long time. Now it has reached 4.1 sigma post-triumph, so I think this is really quite compelling. So Centaurus A is the nearest radiant galaxy of 4 megaparsecs. Then there are some excesses also if we look at the entire, if we look at the expected flux with the entire sky and sort of used as the hypothesis to be tested that the cosmic rays come from jetted AGM. But here there is a kind of weaker signal, still at the pre-signal level. So I think that that's not yet that compelling. There are other sources that have stronger signal. Okay, so those are the observations. Now, there is a possible problem for jetted AGM, and I want to Actually, that's something that started in last time we were at a couple of years ago. So I wanted to acknowledge this, and we did acknowledge it in the paper. But the idea is if we, so this has been done in many previous works, that if you want to have, if one has a population model for the origin of ultra high energy cosmic rays, then what is needed is a good fit between the areas to the diffuse positive spectrum, which is shown here, and to the composition. So this is the average depth of shower maximum. These are the data points. The proton, which is iron, is something that's getting heavier with increasing energy. And so in the majority of these past studies, what was done, because that's a complex thing to simulate, is in order to simplify things to assume standard candle sources. So all the sources are identical in these simulations. And we thought that this is not very realistic. Usually we see huge diversity in terms of luminosity in the population, and that should affect the cosmic ray luminosity and the cosmic ray maximum energy. And so we did a similar study that combined fits to cosmic ray spectrum and composition data, but allowing for a distribution of luminosities and maximum energies. And then we compared what values are allowed in the cosmic ray fit to what we would expect in certain benchmark models. For example, if the maximum energies follow scale as the Lorentz factor distribution of laser jets, which is something that has been measured in individual surveys, like we haven't, or certain luminosity functions for different types of source classes. And what we found is kind of not what one would expect intuitively. So here we parameterize the maximum energy distribution as a power law. Sorry, I should be pointing here with some index beta. And that beta index is shown here. So up here, we have something that goes really fast as e to the minus beta. And here, something which is sort of slowly decaying. And here is what we would expect. Down here is what we would have expected if the maximum energies scale as the, well, okay, we took some different acceleration ones, but more or less down here is what we would expect if the maximum energy scale of the jet Lorentz factor. And we see that this is more than 3 sigma away from the best of our simulations. In other words, it seems that in order to have a good fit for the cosmic ray data, this standard candle picture is required. So either we have sources that are intrinsically identical in terms of what escapes the environment, or it could be also that it is just a handful of sources producing the spectrum above the angle here. That way you don't have so much diversity. So this is why I said this is a kind of variety or a diversity problem for jet data, is because they here we have the kind of broken power law for the maximum energy distribution, and they're all sitting at 2 sigma away from 2 sigma away from our best fit, because the result is rather diverse maximum energies. The only source that we found that sort of is consistent in the 2 sigma with the best fit scenario is Seaford. So let me get to the end, but only marginally. I'll talk about Seafords later. They have other problems. Okay, I'll now switch to neutrinos, and here when we think about high energy neutrinos, the majority of models deal with the blazar part of the jetted ATM population, because they benefit from the same relativistic boost as the photons. So we see boosted ratio, and also because we have these very pairs, which allow for better experimental search. So we have a shorter time window, a smaller atmospheric neutrino background, essentially. And there's tons of work for many years in these. The idea is that protons are being accelerated in the jet somewhere, together with electrons. We have to predict the gamma rays observed. And the question is where exactly this is happening, much like in the DRV, which is if the production explodes to the basically get when it results in PD, neutrinos, which is further away, and the energy of the neutrino is higher because the photon energy is lower. And I think there are compelling observations with more and more lasers, particularly Fermi-lab data, that show that this is a kind of unfortunate thing for us, that the majority of gamma rays are seen to be produced inside the stars, but outside the star light region. That means we expect higher energy neutrinos if the neutrinos are co-produced with the gamma rays, which is usually the simply one zone assumption. Of course, we can introduce multiple zones, then we have more free parameters. It's certain. Yeah, then we can fit more things later, but it's less elegant for now. So ICE has put strong constraints on the emission of neutrinos from lasers via stacking circuits. At the moment, it depends which catalog we use, but at most lasers contribute 20% to the diffuse neutrino flux. But apart from that, apart from the fact that lasers are not the dominant source of large neutrinos, there have been several high energy neutrinos associated with flaring lasers. And here, there isn't all that much new since we had last year's workshop. So I don't have very much new to say on that. But I do want to highlight the power of what we do with this multi-messenger modeling. So what people do is they try to have as much strictly simultaneous, but time simultaneous photon observation of the laser, which has been associated to a neutrino, and they produce models of the electromagnetic and neutrino emission simultaneously. And what this allows us to do is to locate the peak of the neutrino emission, usually with some uncertainty, and an upper limit to the neutrino flux. So, and that allows us to assess whether a particular association makes physical sense or not. And so, for the 4 lasers that we have done before, they are shown here. There are different types of lasers. And usually this is a predicted neutrino flux. Usually that is about an order of magnitude, 2 orders of magnitude less than what would be required in order to produce the one neutrino in ice cube. So that means that not all of these associations can be real. We have a problem with the evidence in bias. Maybe it's a few of them are. And maybe if we once we get more, we will start to see some patterns emerging. One thing I like to highlight is what I was saying before. Since we have these observations of flat spectrum radio quasars, which are the most powerful lasers, unfortunately, there are large redshifts. And we have these observations that the emitting region that's somewhere inside the dust stars. Then we expect neutrinos at energy something like 10 TeV or above. And usually for this kind of sources without extreme parameters with really realistic baryonic loading of the order 1 to the 2, we can get the order half a neutrinos per year. So I think sooner or later we're going to start to see these unless we don't produce any experiments at all, and then we have bigger problems because then we don't have any good other sources. Okay, so I'll switch now to non-jetted AGN. These are not very good gamma ray sources; they are good X-ray sources. So this is these are all the dark red points here are non-jetted AGN in the Swift-Bax catalog. And usually people didn't talk much. I mean, people have talked about these as possible high-energy cosmic ray accelerators, but they're not the main candidate. But in recent years, it has emerged. So known, of course, that AGN have all kinds of different outflows at different scales and with different speeds. But in recent years, it's become clear that about half of them have these ultra-fast outflows. And so these outflows, these UFOs reach about, can reach up to 0.3 times the speed of light. And so if you put the Hillas criterion here, you can get the centralized electron volt charge. The nuclei, so they are sort of plausible, interesting sites for ultra-high energy cosmic ray acceleration as well. And this was looked at in some detail by Peretti and people at the NTNU recently. And what they found is that usually you could accelerate protons, especially for protons, only up to more than 10 to the 18 electron volts. But the maximum energy that escapes is is limited by these photon fields. So the acceleration is happening now inside the AGN, and you see the escaping spectrum, which is this one, is severely depleted with respect to what was accelerated in the shock produced by the UFO. Recently, we've been doing this also for nuclei, and we're unfortunately seeing that we're not really gaining a factor of Z. So the photon fields are really problematic. So at most, these energies are interesting in the actual region of the cosmic ray spectrum, but they don't seem to reach the highest energies. Now, these AGN are excellent candidates for neutrino production because they have these photon fields, the field from the disk and from the corona. And so there were early models on this by people like Stetter, where the neutrinos were predicted to be in the PeV energy range. In more recent models, mostly by Pacal, which show that you can also have neutrinos in medium energies, around 10 keV and below, associated with the corona region of the AGN and the corona photons. So in principle, at this moment, it's possible to explain all of high-speed neutrinos with these non-jetted AGN, and there is no observation that sort of speaks against that. That's certainly possible. There is in stacking, has looked, and in stacking they actually find the signal. It's very weak, right? It's only 2.6 sigma. But if we interpret this as a real signal, then that explains the higher energy part of the spectrum, so around 100 PeV and above. And that particular analysis doesn't deal with the medium energy neutrinos, which is also where NGC 1068 is. And what is interesting is that their best fit spectral index for the neutrinos is e to the -2. So it goes all the way up to the highest energies. Now NGC 1068, you might expect we've all heard of it. So this is nearby one of the nearest Seymour galaxies. And so the excess of neutrinos that IceCube sees, if you look anywhere in the northern sky, you're killed by a ground factor, 2 sigma. But because it is a prism that is sourced from a catalog, the significance of the observation is at the 4 sigma level. If you look only at the trial associated with the catalog sources. So this is the spectral energy distribution that is inferred for the source. I'll show this here. The peculiar thing about NGC 1068 is that this is the neutrino spectrum, and these are the gamma rays. And the peculiar thing is that there are up to a factor of 100 more in neutrino flux than in gamma ray flux. And in order for this to be possible, because usually it's called the fine production, we produce one the same flux of neutrinos of gamma rays. What needs to be happening is that the emission has to be coming from the core of the AGN, but that the gamma rays are blocked when the neutrinos escape. And this is more or less consistent with what everybody is finding here, even though this was all work pioneered by Kota before this signal was as high as it is today. Now I'll come to tidal disruption events. So these are also very bad gamma ray emitters. So we've looked, other people have looked, there is no gamma ray signal. But this population is really growing. So and that's thanks to mainly optical service transient facilities. So at the moment, we have maybe 200, more than 200 known tidal disruption events, which is quite a lot. A few years ago, we knew only a few tens. People have looked for neutrino signal in stacking from tidal disruption events. Unfortunately, there is nothing there. So for the non-jetted DBs, that translates to very strict upper limit to their contribution to the active neutrino flux in the order of 3%. And for the non-jetted ones, the limit is more loose because there are more sources, and so the order 30%. And there are these three DBs that have a counterpart, and they have a neutrino, high-energy neutrino associated with that. And what is, so that's the combined significance of the 4 sigma level, a little bit below. But what is sort of interesting here is that for all of the events, the neutrino came 150 days or more after the PDE, which is peculiar. Usually, most of the, but we do not know when and if an officially forms in all PDEs, but generally this delay was not particularly predicted by any model, so it's a bit odd. The 3 PDEs that were associated with an neutrino didn't have a jet, and that means that the models that have been explored rely on a disk wind or outflow in the disk region, which provides the acceleration side, and then the corona and the disk photons for defining interactions with stimuli to the NTNU model. Now, previously, we really didn't have enough data to do this similar thing for PDE as for blazars, but we're starting to get more data. So you see here 2 scenarios for the neutrinos and the accompanying electromagnetic counterpart. So had we had nicer pointing to this PDE, we would be able to rule out the corona model or to detect something else, just the sensitivity here. We didn't point at that time. And so I want to finish with some interesting developments in terms of PDE observations. So one thing that came out a week ago is an example of a PDE which rebrightens in the X-ray 200 days after the optical peak. And it has the associated ultra-fast outflow with a velocity about 0.1 times the speed of light with it. That's one thing which I think is interesting, related to the acceleration of particles. They suggest that this because they found this serendipitously, but maybe this can be present in a large fraction of PDEs. And there was this other work in which they found that there are ubiquitous radio outflows up to 10 years after the onset of the PDE. These are subrelativistic. Now, I'm not suggesting that this tells us that there is neutrino production 10 years after the TDE, but what I think is interesting is that we're starting to have the ability to produce much better models, which will eventually allow us to do the kind of thing we've been doing for blazars for these transients which were not so well known previously. With more observations we collect. And recently we've been awarded some time on NewStar with Pascal, with Jean, to follow up gold neutrino alerts. And so the idea here is that we will be able to really test neutrino production models with as much as possible the multivariate coverage, starting with these hard X-rays. Okay, so I think I'm finished. So let me just summarize. My message here is that I think that jetted AGN are very promising, both as ultra high energy cosmic ray sources, and maybe we're soon going to start to see finally some compelling evidence, and also as neutrino point sources at about PV and above. And non-jetted AGN, we're starting to see evidence of neutrino emission. Unfortunately, that's not transient. So at least they haven't been more looking at the transient nature of the signal, but the monetized is too small for that. But further in the future, that will be an interesting thing to look into as well. And finally, in terms of TDEs, I'm personally very excited that we are collecting new observations, we're learning more about these objects, and eventually we'll be able to have much better messenger models for these and sort of specify better where the neutrino emission might be coming from, maybe even being one of the results of this community.